Hey everybody, welcome to the fourth quarter. I hope everyone had good breaks because we're going to hit the ground running today. I want to talk to you a little bit about our unit on geologic time, kind of outline what we're going to be doing this quarter, what's going to be expected of you, and what topics we're covering, especially for this first homework assignment. So just an overview, we're going to have 2 unit projects, 2 labs, 1 case study, quite a few homework videos, and a few homework worksheets to go with those videos. As always, we'll have the textbook sections posted with the videos. A few of them, though, you'll be required to watch the video instead of read the textbook section because you will be absolutely unable to do one of the assignments unless you watch the video. So keep your eyes on that and make sure you're updating your portfolio as we go, especially because you're going to start losing your motivation here in the fourth quarter. So make sure you keep your portfolio up to date. So geologic time, that's what we're going on for this next unit. So I'm going to start this one out with why it matters. It's actually interesting. In your textbook, it's like the 13th section in this unit, but I want to start it out by explaining to you why we even do this. So the reason we want to understand the sequence of events in geologic time and how old the Earth is, it has quite a few roots. For instance, geologic hazards. We've talked a lot about volcanoes, but knowing when a volcano has recently erupted and the order of operations for that is kind of important because if you look at this image here, one of these volcanoes has a relatively fresh deposit and one of the other volcanoes has a relatively old deposit. So knowing which volcano was more recently active can help us tailor our observations, our monitoring tools, and help warn people when an eruption is imminent. For earthquakes, actually, what you see here is this is an outline of a fault, and this one's a relatively recent fault, and the one over here that I'm outlining here is a relatively older fault. So this helps, just like with the volcanoes, this helps us figure out, okay, what was the most recent earthquake and where was it? Over here, the last image on the bottom here, this is a floodplain, and knowing when floods happen and where they happen is really important, especially for areas in the southeast, which are particularly flood prone. The order of operations and the history of an environment can also be really helpful for natural resources. That's this section over here, these images. We're going to get a little more into these farther along in the unit, but I want to outline knowing when say a granite intrusion has come up, that's going to affect how many minerals you're going to find. So if we remember from our igneous rocks unit, granite intrusions can oftentimes lead to deposits of gold or silver. And if you know a granite intrusion is pretty old, then you might have more gold and more silver as opposed to it being relatively young. The order of operations can also be really important when you're looking for things like gas and oil. We talked a little bit about shale and caps in our sedimentary rocks unit, and the sequence of events in terms of the amount of groundwater you're likely to find in an area can be pretty important because if you know how much groundwater is in an area, you know what a normal amount of groundwater is, and you can kind of back out, okay, do we have a normal amount? Are we entering a drought? Are we exiting a drought? That can be pretty important. And these last 2 images, I like these. These tie into human history or the history of the Earth. So we can use radiometric dating techniques, which we'll get into a little later in our radioactive decay lab. We can use those to look at the the absolute ages of things to figure out, okay, when were certain types of humanoid species active and when did certain events happen in Earth's history. So it's just to give you a sort of a justification for why we learn what we learn, right? Okay, so let's talk a little bit about hold on, let me pause for a second. I'll be right back, guys. All right, guys, I'm back. You wouldn't have seen that as any change in time, but I had a small PowerPoint issue. So I want to talk a little bit briefly about the 5 main principles we use when we're looking at relative age. Now, relative age is what it sounds like. It's just comparative age between different layers, okay? And we use a bunch of ideas here that oftentimes a lot of these seem pretty obvious, but we like to lay them out kind of formally. So when you're looking at different layers of rocks and you're trying to find out the relative age, like which one's older, which one's younger, you use these 5 principles to break this down. The first one is the law of original horizontality. And that's what it sounds like. We suppose that rock layers are deposited horizontal and they become tilted or angled because of events that happen. So if you look at the image on the right, you see all these really thin horizontal layers. Now, if you look at the images on the left, it's actually quite a few different angled layers. And if you look just at this section right here, we assume that those layers were deposited horizontally, and whatever event tilted them had to have happened after they formed. Okay, so you can actually infer different events and different depositions between these two layers, okay? Now, if something were to happen to the images on the right, or the layers on the right, and they tilted later, then we can infer that the event that tilted them happened, of course, after the layers were formed. Got it? So the second principle is the law of superposition, and that is the idea. And again, this one's one of those like, well, duh ideas, but we like to lay it out to be really formal about it. It's the law of superposition, which states that layers on the bottom are the oldest. So we have an order of events here. This is time point 1, this is time point 2, and this is time point 3, and we say that the gray layer on the bottom must be the oldest, and over time, the layers above it formed later. This might seem obvious, but if you're a geologist and you go out in the field and you start taking absolute age dates where you actually do radioactive dating and you find out, let's say you actually find out that the layers on the bottom are younger, well then you know that something major must have happened. It must have completely overturned the rock layers. So just an example of this, if you look here, oh look, all my writing's still on the screen. I'll erase it. If you look here, these are these layers on the bottom here, and we can assume that the youngest layers are down here at the bottom of our what looks to be the Grand Canyon. Same thing here. If we look at these, if we want to figure out where the oldest layers are, we would say that the oldest layers are on the left side of our image. We would say that these are the oldest and these are the youngest, okay? Because we assume, based on our earlier principle, that the layers were deposited flat and then tilted later, okay? All right, the third principle is a little harder to conceptualize, but it's called the law of inclusions, which states that you can have younger layers that contain pieces of older layers. And so what we have is a situation here, we've got these really interesting rock layers here. These are metamorphic rocks, these dark ones. They were included in this lighter, younger rock, which is granite, okay? And this here is an older metamorphic rock. And what this allows you to do is you can say that if your granite includes the metamorphic rocks, then the metamorphic rocks had to be older because the metamorphic rocks had to form, then be included in the younger rocks. So what you can kind of take away from that is that if you have pieces of a layer contained in another layer, the pieces must be older. They had to have been formed first in order to be picked up by the second layer. So so this rock, this is actually a really good image here. This is older rock here. This is actually basalt. And you can see little pieces of it kind of included in this tan rock. So this rock on the bottom of my image here must be older than the rock above it because this rock above it picked up little pieces of it. Kind of like if I wanted to say walk over to Joey and steal his pencil, Joey had to have acquired his pencil first in order for me to steal it. That's just a joke. We know Joey would never bring a pencil to class. Come on, guys. All right. Law of cross-cutting relationships. This is another one that says if you've got layers that have little features cutting across it, then the layers that are being cut across must be older. They had to have been there in the first place, and then the stuff that cuts across it has to be younger. So look here. I like this image. This is a really neat image because it's got lots and lots of layers, but you see all these fractures kind of running across it. These fractures have to be younger than the rock they cut across. So if I like to highlight this one fracture right here. This fracture must be younger than all these layers it cuts into, but look, it stops right here. So it has to be older than that rock right above it. So we could infer the order was first these layers formed, then this fracture formed, then this layer formed above it. Okay, so the law of cross-cutting relationships states that features that cut across, I can't spell, you all know that. Features that cut across other features have to be younger. Okay. And finally, the last one has to do with contact. And actually, if you were on our, what's it called? If you were on our Sibley trip, we actually looked at a lot of these layers. This is the law of contact effects. And it basically states that layers that cause contact effects with other layers have to be younger. The best example here is lava, and lava creating baked layers. So if you see here, this right here, this is a lava flow in the image, and it is causing a baked effect on the rock around it. That means that that baked layer had to be older. It had to be there in the first place in order to be affected by the new layer. Same thing over here in the left image. We've got sorry guys. We've got a layer down here that's causing a baked zone to form, and then you've got other layers up here that are sedimentary. Okay, and so this layer must have baked, this layer on the bottom must have caused a baked layer effect, okay? So anything that is baked by a lava flow must have been there in the first place in order to be affected by the lava flow. A lot of these are kind of common sense things that we tend to know about, but it's good to sort of lay it out and clarify what it means, okay? So your homework tonight is to lay out those 5 principles and then apply them in an image. It's kind of an interesting one. So apply them. I want you to apply those principles and put the order of I want you to apply these principles to an image that has multiple layers, and I want you to put those layers in order of formation from, I believe it's oldest to youngest. That's kind of how we do things. The worksheet is in OneNote, and I handed it out in class. So please get that done, and I will see everybody tomorrow.